Okay, so now that we've got the driving part, we're ready to add the turning part. So we need to think about the logic of this first. So let's take a look at the gamepad and remember that we're going to be turning with the right joystick and moving it right or left. If we move this joystick to the right, we want the robot to turn right. So looking at the robot, this means the left wheel should be turning more and the right wheel should be turning less or maybe even turning backward. If the right wheel turns all the way backwards and the left wheel turns all the way forward, we're going to pivot to the right. So it's kind of thinking about that logic. I know that this way is +1. So this is a positive number. If I add this number to the left wheel and subtract this number from the right wheel, we'll turn right correctly. So now I'm thinking maybe what I need to do is add this number to the left wheel and subtract it from the right wheel. Let's think about if this logic still holds if we move the joystick all the way to the left. So in this direction, x is -1. So originally I was thinking maybe I add this to the left wheel and subtract it to the right wheel. Would that make me turn right if would it make me turn left if I go this way? So if I take -1 and add that to the left wheel, that would make the left wheel go to -1, so it would go backwards. Taking -1 and subtracting that from the right wheel, now you're subtracting a negative, which, wait a minute, is the same thing as adding a positive. So you'd basically be adding to the right wheel. So if you want to turn this way, you would add to the right wheel, you'd subtract from the left wheel. That means the right wheel would turn more and we would actually turn to the left. So that's exactly the behavior we want. Whatever value we get from the x-axis, we're going to add it to the left motor, and we're going to subtract it from the right motor, because if you subtract a negative, it's the same thing as adding a positive. Math. So we already are getting that value from the gamepad, and we're already finding the power from the left joystick. So now we're going to adjust that power by adding the value of the right joystick to it. So we'll say left power equals left power plus right x, and right power equals right power minus right x. Notice I've got the capital P in both and then the capital X in the word right x. Finally, one thing to think about is that the motors have a maximum power value of +1 or -1. So from this math, the highest value I can get is +2 and the lowest value I can get is -2. We need to peg it, like max it out at +1 and -1. So we're going to use a function called clip. And clip will just clip the range, so it's only a max of 1 and a min of -1. So what we do is we say left power equals capital R range dot clip, and we're going to clip left power to be a number between -1.0 and 1.0. Same thing with right power. Range dot clip right power -1.0, 1.0. So even we can't like overshoot our power range on the motors. The motors might still work even if you give them a number that's too high, but I'm not totally sure. So now when we build everything, we should be able to drive and turn. Now before we build everything, because this is a pretty simple thing to do, I'm going to go ahead and add the code for the servo. So the way to do this for the servo is we're going to use the buttons on the front of the gamepad. Okay? On the front of the gamepad, we've got 4 buttons here. These buttons up on top are the right and left bumpers, and the buttons right below them are the right and left triggers. We're going to use the right trigger. The right trigger returns a value between 0 and 1, 0 being not pushed at all, and 1 being all the way pushed in. So I'm just going to write code that shows if I get a value greater than, say, 0.5, let's put the arm down. You could make it very adjustable so the arm goes like variable amounts down depending on how much this is pushed. But I'm just going to make it go all the way to 90 degrees when I push the button a little. So the way I do that is with an if statement. We noticed earlier in the code there's a structure called a while statement, and if statements are going to look very similar. So first we'll get a variable, double right trigger, and we're going to set that variable by reading the value from the gamepad. Right trigger equals gamepad 1 dot right underscore trigger. So now it's a value between 0 and 1. And here's where we'll do our if statement. The way an if statement works is you write the word if, and you have a condition in between parentheses. In this case, the condition will be, I'm going to check to see if the right trigger value is greater than 0.5. And we have to write this with symbols, not write it with words. Right trigger is greater than is an operator that you do with the little is greater than symbol, 0.5. And the parentheses, no semicolon yet. So as long as this condition is true, if the right trigger is greater than 0.5, we'll do a set of curly braces. Notice if I do an open curly brace, see how it adds the closed curly brace automatically and it's indented at the same level as the curly brace above it. So that's kind of helpful. We'll do claw.set position 0.5. So one thing I notice about this code is if I push the trigger, it's going to lower the claw to 90 degrees, but there's no provision to like raise the claw back up to 0 if I let go of the button. So if I want it to raise the claw back up, what I'll do is I'll add a second part of this, which is the else, and then a set of curly braces. So it should have added the closed curly brace for me, and it looks like it did. So if the right trigger is not greater than 0.5, then we'll set the claw position to still just be straight up again. Claw.set position 0.0. Okay, so if we've pushed the button, it will lower it to 0.5. If we release the button, it puts it back up at 0. Again, pay really careful attention to capitalization, punctuation, spelling, all that fun stuff. If it looks good, click the wrench. You'll know pretty quickly if you spelled anything wrong. And it looks like the build succeeded. And so now, when I go over to my phone, I can hit the right arrow button, pull down that same function, Gamepad Drive, hit init, hit play, and then I should be able to use the gamepad to drive, steer, and also use the claw. Okay, now that we've got a driver-controlled mode working, we're ready to work on autonomous mode. So in autonomous mode, the robot will drive by itself. You're expected to hit init at the beginning of the match, and then you sit there and wait until the judge gives you the signal. Then you'll push play, and it's completely hands-off. For 30 seconds, the robot runs all by itself, doing a few tasks. Autonomous mode was one of the trickier things that my team learned about in our first year, so I want to show you how to write your first autonomous mode program. And all this one will do is drive, turn, drive again, and lower the claw. But with the basics of learning how to drive and turn, you should be able to string together a pretty complicated autonomous mode program. And you also can use some of the same principles, like programming with an encoder, in your driver-controlled mode if you want to use something, say, a little more powerful than a servo. So let's get started. To add your first autonomous mode program, you're going to go back to the File Explorer and use the plus button. Click Add File. And then to give it a name, we'll name this one Auto Drive, just to give it a name that you can remember. And then make sure it's going to be in the team code folder. That's really important. This one will be autonomous. We do want to set up the code for the configured hardware. And we're going to base it off of a blank linear op mode as before. It's just an autonomous op mode this time. Click OK. All right, so now we get our new code here. So just as before, there's a bunch of libraries imported. There are a few more libraries than there were before. And then if we scroll down, you can see there's another class, and the class contains properties, and it contains a method. So just as before, this sets up your data, and then this is the behavior. And the behavior, most of the behavior is going to run inside this while op mode is active. Anything before you hit play is done before wait for start, and anything after you hit the run button is done after wait for start, preferably inside this while function. To make our life a little bit simpler, so driving with one of those DC motors using the encoder involves a ton of steps, and it's helpful if we just enclose that whole bunch of steps that's required to like drive using the encoder into one function. So we're going to learn how to add another method into the class. Just like public void run op mode is a method inside the auto drive class, we're going to add another method, and we're going to call it Encoder Drive. So I'll add a few lines below this curly brace, but it still needs to be inside the very last curly brace, the one that has the whole class inside it. So basically right before the last curly brace of your code, this is where we're going to put the encoder drive function. So we can even make a little space for it. Private void encoder drive. And encoder drive is going to need 4 pieces of information. We'll do a speed. We'll include how many inches we want the left wheel to go forward. We'll include how many inches we want the right wheel to go forward. And then we'll include how much time is needed to complete this task, an estimate. This is basically our timeout time, so if we don't finish the task in that time, it'll bail out of the function. So double timeout S for seconds. And we do an open curly brace, and there should be added automatically a closed curly brace below it at that same indent level. So this will have all the code that's needed to drive the motors a certain number of inches forward or backward on each motor at a certain speed. Before we write that code, one thing we're going to add to our data members inside this class are some variables that just represent some like math for driving. So we can calculate, basically the encoders work by kind of counting how far it's moved forward, kind of like it counts teeth in a gear. It has little electronic ticks inside it that it'll move forward and backward as the motor rotates. And so you want to move it forward or backward a certain number of ticks. And we can do some math to translate that number of ticks to inches on your wheel. And this is how we do it. We're going to make one variable, and I'm just going to put some fancy words in front of it, so just, don't worry about these. Static, final, double. So it basically means this, this variable is staying what it is, no matter what part of code is using it, everywhere, forever. Static, final, double, counts per rev equals 1440. So for the Tetrix motors that we're using, they have 1440 counts every revolution. Our drive wheel is also geared at a 2-to-1 ratio, so we're going to multiply that times 2. So here's where we'll put static, final, double, drive, reduction equals 2. Next, we're going to add static, final, double, wheel diameter. And the wheel diameter on those basic like plastic wheels that come in the Tetrix robotics kit are 4 inches in diameter, measuring across. You'll just plug in whatever the diameter of your wheels is. I plugged in 4.0 because my wheels are 4 inches across. And then here's where we do a little bit of math. So we know that these wheels have 1440 ticks per revolution, but we multiply that times 2 because there's a drive gear reduction in there. And we know our wheel diameter is 4 inches across. So we can figure out how many inches the circumference of the wheel is by taking the diameter and multiplying it by pi, because diameter times pi is circumference. So the circumference of the wheel is 4 inches times pi. If we take the number of counts per revolution and we divide that by the circumference of the wheel in inches, we'll get the number of counts that we need to go by in the motor in order to get 1 inch. So that's the value we're looking for. We write static, final, double, counts, underscore per, underscore inch. I'm doing all caps just to show this is a really important variable. Equals counts per rev times drive reduction. And then all that is, see, I put it in parentheses because we're taking that whole quantity and dividing it by the circumference of the wheel. So in another set of parentheses, we'll do wheel underscore diameter times, and it's a little hard to see because of the wrench in the way, sorry, 3.1416, which is approximately pi. And I'm going to do a semicolon right there and hit enter, and let me just make sure you can see that whole thing. So counts per inch is the counts per revolution times the drive reduction, so it's 2880, divided by the number of inches in the wheel's circumference, which is, which is wheel diameter times pi. Okay, and after we do all that math, that counts per inch is the final result there. So this is, I can't take credit for all of this. This was, it's located in one of the example files for autonomous mode, but I found it really helpful just to go through that exercise and kind of think about it. So we've got some important variables set up. We are go ahead and ready to write our encoder drive function. Now here I'm going to make life a little bit easier for you, and I'm giving you some code in the caption of the YouTube video that you can copy and paste into Encoder Drive. So go ahead and copy and paste that code, and then we'll come right back and explain what the code is and what it does. All right, welcome back. So we're going to go back into Auto Drive, our function that we just created, and we have made this function called Encoder Drive, and there's nothing in it right now. So I copied the code that we need to paste in there. I'm going to make sure I'm in between the two sets of curly braces, one here and one right down there, and inside the two sets of curly braces, I'll do Control-V to paste. So in this, and it's a good thing we had this chunk of code here. It looks like I accidentally captured some additional curly braces, perhaps. Let me check and see. So checking for matching curly braces is a really important part of programming. So I'm going to start from the most indented set of curly braces and work my way out. Here's a while loop, and there's a condition inside a big set of parentheses with a curly brace and then a matching curly brace here. Going outward from there, here's an if statement with a condition inside the parentheses. Here's the open curly brace, and the closed curly brace for that one is right there. And then at the uppermost level, here's the name of the method, Encoder Drive, the curly brace that starts that method. And then if I go down all the way, here's the curly brace that ends that method. This last completely outdented curly brace matches the beginning of the function. So I think we're good. We have all of our matching curly braces. Okay, what this function does is basically we get the positions of both encoders at this moment in time right now. We calculate what the position should be if we move the motors to the desired position a certain number of inches away, and then we program the motors to move until they get to that position. So these two variables are called new left target and new right target, and then we calculate what those are with this math formula. So we find the current position of the left motor, for example, and then since my left motor is moving in reverse, it's moving backwards, we subtract the number of counts from the left motor. So we're going to subtract inches times that variable that we declared way up top in the class, counts per inch. So for example, if we want to go 3 inches, we'll figure out how many counts it takes for 1 inch and multiply that times 3, and we're going to subtract that number of counts from the current position. So we're going by encoder counts. We do the same thing with the right motor, but since my right motor is moving forward, then we're going to add that number of counts to its current position. So we do current position plus right inches times counts per inch. Make sense? Next, we're going to program the motor encoders with the desired position that we want. So we say set target position on both motors. We go to set mode, and we're going to turn both motors to the mode run to position. This runtime.reset is what we use to set a timer, so you don't need to worry about it too much, but it's going to be used to do just some timeout functionality. We set the power, and that's just simply the speed parameter that we're passing into the function right here. So when we call the function, we're going to give it a speed, and then that speed is used right here. Math.abs is an absolute value function. So if you set a speed that's negative, for example, it's going to automatically convert it to be positive, since our motors are already configured to run forward and backward or whatever the correct direction is. So this is where so it resets the runtime timeout, and then in here, this is where it uses that runtime object. So it'll check to see how many seconds we've been running, and then as long as you've been running a fewer number of seconds than the timeout that we send to the Encoder Drive function, then it will keep running. But if it takes too long to run to this position, it's just going to stop and bail out. It's just something that prevents your robot from running forever if it's stuck. So in this while loop, we check to see 3 conditions. Is the op mode still active? Have we not reached the timeout yet? And are both motors still busy? If all 3 of those conditions are all true, then it's just going to add telemetry data and just keep going. But if any one of those conditions becomes false, either you've turned off the op mode, or the timeout was reached, or the motors are no longer busy, so they've got to their destination, then you drop out of the loop right here, and you're going to set both motors to power 0. You're going to put them back in their initial mode, and we're going to send telemetry data saying the path is complete. So that's how the function works. And now all we have to do is use this function to drive to whatever destination we want to. So going back into the main part of the code, here's the method run op mode. I'm going to do one quick thing before I change that code. And up here, we've got, there it is, that little autonomous, and I'm going to give it a name that I can call from the phone itself. So I'll add the name attribute. Name equals, we'll call it auto simple. Okay. So inside the code down here, we have the initialization that'll happen before wait to start, and then we'll do the encoder drive calls inside. Actually, I think we can get rid of while op mode is active and just replace this whole thing with the encoder drive functions. So grab this while op mode is active, find the open curly brace, find the closing curly brace, and then it can go away. There's a little comment which is kind of irrelevant now, so that comment can go away as well. All right, before we do the wait for start, let's set the servo to its starting position. So we'll do claw.set position 0.0. Okay, and then let's go ahead and call encoder drive to move, and then we'll do claw.set position to move the claw. And it's really simple to use encoder drive now that we've done that work to write the function. So what we do is we do encoder drive, and inside the parentheses, we're going to use 4 numbers. Let me scroll down a little bit so I can see them one more time. A speed, the number of inches to go on the left wheel, the number of inches to go on the right wheel, and then a timeout in seconds. So for speed, I'm just going to do 1.0, so we go full speed. And then for the, let's go straight first, so the left and right inches will be the same. We'll go like 1.5 feet. 18.0 inches, 18.0 inches. And then for the timeout, let's give it, let's say 5 seconds to get there. Hopefully it takes less than 5 seconds to go 18 inches. Then we'll turn. So we do encoder drive 1.0 for the speed. And then let's make this a right turn. So the left wheel is going to go 12 inches, and the right wheel will go negative 12 inches. And we'll give it 5 seconds to complete that task. Then we'll drive straight one more time. Encoder drive 1.0. Let's go 24 inches this time, so full 2 feet, 24 inches again, and we'll give it 5 seconds to finish that task. And then lastly, we'll drop the claw. Claw.set position 0.5, so it goes down 90 degrees. That's it. Once you've got encoder drive written, driving and making the claw move are just as simple as every time you want to make a driving move, you add 1 line of code. Watch the spelling, watch the semicolons. It's not any harder than that. So I think we're ready to go ahead and build. Let's click the wrench. And it looks like it had 1 error. See, this is a classic one where I would first think that I have a spelling mistake, but actually I know what this issue is. It says it cannot find a symbol and the variable's name is runtime. So in here, I very brazenly used a function called runtime right here. And I also used runtime right here, but I didn't actually say what runtime is or declare it. So since everything is inside this class right here, auto drive, I'm going to add a data member that is named runtime, which is the elapsed time that the program's been running. So we'll say private elapsed time runtime equals new elapsed time. So it'll make a new object called elapsed time and name it runtime. So I put this, and I'm missing a semicolon. How could I? Put a semicolon right there. No wonder it had a red X. So in our data member section inside our main class, we've got all these different data members, and I just added 1 more, which made an elapsed time object that we can use to keep track of how long our robot's been running so far. And then this is important so we can use that timeout functionality. Okay, wrench again to build everything. And it says the build succeeded. So now we're ready to go ahead and test it. So our robot will drive, turn, drive again, and then drop the claw. Okay, for our final mini lesson on coding, we've got 2 minor changes to make before we are ready to ship this. When you tested this code, if you tested it on your own, you may have noticed the claw didn't fully drop at the end of the path. So the reason why it didn't fully drop is that it ran this code for claw.setPosition. Then the code got to this curly brace and it quit. And it may have quit before it fully dropped the claw into position. So to make sure it drops fully, just add a little pause, like a tiny delay, just to give it enough time to actually drop the claw. So we can use the sleep command, sleep, and then the parameter that it takes is the number of milliseconds to sleep. So 1,000 milliseconds is equal to 1 second, and that's more than long enough for it to drop the claw. So if you have a task at the very end of your code, you may want to add a short delay so that that task can finish. Second thing, one thing we ran into at competition, which was devastating to find out after the first couple runs of competition, is that we had a timeout issue. So this is what it looked like. We'd get the phone, and it's supposed to start in autonomous mode. We'd queue up the program, we'd hit init, and then the robot would sit there in its initialized state, waiting for the judges to have everybody ready so that the students could hit the play triangle. And sometimes this took a while. So we'd be sitting there for 3, 4, 5 minutes in initialized mode, just waiting for things to get started. After that 3, 4, 5 minutes, when we hit the play button, the robot didn't work anymore, or the play button went away and it was back to the init state. So this was really frustrating, and you're not allowed to touch the phone when the robot's in autonomous mode, so we just missed the autonomous section completely. What was happening was the phone was just kind of going to sleep, and that was happening during this little function here, wait for start. So wait for start had some kind of timeout built in that was shorter than the amount of time that it took for the judges to actually let us push the play button. There's a workaround, which we found by doing some searching while we were at the competition and adjusting the code there, but it was something that really took us off guard and caused us to blow a couple of matches before it got figured out. So here's what you do. We got the example code from the GitHub site for First Tech Challenge, and there's a little troubleshooting section. And the troubleshooting section has a whole troubleshooting page around this timeout for the Motorola E4 phones. So it may only be an issue with the Motorola E4. It may affect other phones, I'm not sure. So what you do is, instead of the wait for start line of code, you just replace wait for start with these lines of code. And all they do is they just send telemetry data over and over again until you hit the play button. So it just kind of keeps the phone busy while you're waiting. You can just copy this, and again, I'll put this code in the caption of the YouTube video so you can paste it into the code if you find you have this problem. And then you can paste it into your code here. I recommend you just put 2 slashes before that line just to comment it out so it's still there if you want to use it. And then this is going to be the code that will actually run. So as long as the op mode is not active and you haven't stopped, then it's just going to send telemetry data. So that should keep the phone alive for as long as you need to until it's actually time to hit the play button. Okay, test out your code. Make sure it works and runs your robot to its final position correctly. Great job at finishing this tutorial. I hope you have a wonderful season. And if you have any questions on First Tech Challenge things that you think that a fairly rookie team could help you answer, please feel free to leave a comment. Thanks.